The speed of aircraft increased dramatically during World War II. After the war, the quest for speed continued, but was stymied by a sound barrier, an aerodynamic phenomenon that resulted in loss of aircraft and pilots. The wind tunnels at that time could not provide accurate data near Mach 1. The only means available to understand the unknowns facing pilots at transonic and supersonic speeds was to build specialized research aircraft with enough structural strength to withstand the unknown forces. With its ideal flying weather, the Muroc Army Airfield in Southern California was the perfect location for operating these research aircraft. Rogers Dry Lake, with an area of 44 square miles, served as a runway that stretched for miles in any direction. In September of 1946, the first group of engineers from the National Advisory Committee for Aeronautics, or NACA, arrived at Muroc. They were to assist the Army Air Force in a supersonic flight program involving the XS-1. Their new home was much different than the one they had left in Virginia. The facilities were as rugged as the desert landscape. Initially named NACA Muroc Flight Test Unit, the staff had a single hangar and lean-to offices, while housing consisted of wartime barracks. Some personnel left due to the harsh conditions, but those who stayed established a tradition of innovation and creativity. The Bell XS-1, its fuselage patterned on the lines of a .50 caliber machine gun bullet, was designed to fly at speeds in excess of Mach 1. The Air Force, with NACA support, conducted an accelerated test program with the first X-1, with the goal of quickly reaching Mach 1. The rocket-powered XS-1, later redesignated X-1, was carried aloft by a modified B-29. As the B-29 climbed to altitude, the XS-1 pilot entered the cockpit. On the historic day of October 14, 1947, Captain Charles Chuck Yeager, seated in the XS-1 as it dropped away from the B-29, lit the rocket engines. As the plane accelerated, it pulled away from the P-80 chase plane, trailing a long white contrail. As the speed increased, the Mach meter needle passed 0.98, then suddenly jumped off scale, signifying supersonic flight. Captain Yeager had become the first person to break through the sound barrier, piloting the XS-1 to Mach 1.06. NACA flew the second X-1 in a more cautious step-by-step build-up program. Herbert Hoover, not the 31st president, became the first civilian NACA pilot to reach Mach 1 on March 4, 1948. Originally painted orange, the X-1s were repainted white for better tracking visibility against the blue sky. This remains the case even today for most research aircraft. The X-1 program laid the foundation for NACA's and later NASA's flight research. Other aircraft exploring the transonic region of flight included the Douglas D-558 Phase 1 Skystreak and Phase 2 Skyrocket in a joint NACA-Navy program. The Phase 1 was a conventional 1940s design with a turbojet engine to explore the transonic regime. Vortex generators, seen now on many military and commercial aircraft, were first developed on the D-558 Phase 1. The D-558 Phase 2, in contrast, was a swept-wing aircraft designed to explore supersonic flight. Though turbojet and rocket-only versions were built, the rocket-only version of the D-558 Phase 2, launched from the B-29, was much more productive, gathering supersonic research data. Though it was against NACA policy to set speed or altitude records, Scott Crossfield convinced management to attempt an assault on Mach 2 with the D558 Phase 2 rocket-powered skyrocket. In preparation for its record flight at the edge of its envelope, the skyrocket was fitted with engine nozzle extensions for more thrust. The skin was waxed to reduce drag, and the aircraft chilled to allow more fuel to be carried. On the cold winter morning of November 20, 1953, after the skyrocket dropped from the B-29, Crossfield lit the rockets and climbed to 62,000 feet. Flying a perfect flight plan, he piloted the D558 Phase 2 to its maximum speed of Mach 2.005 and became the first man to exceed twice the speed of sound. Versions of the X-1 continued to perform high-speed flight research. The most notable one now sits on a post in front of the main building at Dryden. It is the X-1E. It was modified in-house from the first NACA X-1 to conduct research on very thin wings at high speeds. It first flew in December 1955 and continued Mach 2 flights to the end of 1958. While the rocket-powered aircraft attracted much of the public's attention, these were not the only research vehicles being tested in the 1950s. Some of these revolutionary vehicles looked rather strange, even by today's standards. One such example was the Douglas X-3 Stiletto, which was developed to test very thin, low-aspect ratio wings at high speeds. However, the planned high-thrust jet engines did not materialize. It was severely underpowered with the substitute engines. It was difficult to control and could only reach supersonic speed by putting the aircraft in a deep dive. Although not entirely successful, the X-3 did make significant contributions. Similar wings were used successfully on the F-104. The X-3 was one of the first aircraft to use titanium. Its incredible high landing speed of 260 knots also necessitated the development of high-speed aircraft tires. The Northrop X-4 tested a semi-tailless swept-back wing configuration. Engineers hoped that eliminating the horizontal stabilizers would ease control problems at transonic speeds. But at speeds approaching Mach 1, the aircraft handled poorly. It was likened to driving over a washboard road. This configuration would prove to be impractical until the arrival of digital flight computers 20 years later. The Bell X-5 was designed to test the feasibility of changing the sweep angle of an aircraft's wings in flight. Such a capability would give an aircraft good low-speed control with the wings extended, while at high speeds, the wings could be swept back to reduce drag. An extensive flight test program with the X-5 showed these predictions were justified, and the concept has since been used successfully on aircraft like the F-111, F-14, B-1, and others. This first decade of flight research at Muroc was an exciting period with many milestones achieved and signaled the bright future to come. As the quest for speed and altitude continued, the Air Force, Navy, and the NACA, later NASA, contracted with North American Aviation to build a new vehicle. This new vehicle, the X-15, would probe the hypersonic speed regime, that is, faster than Mach 5, and perform flight research at the edges of the Earth's atmosphere. To perform its mission, the X-15 structure was made from a nickel-chrome alloy called Inconel X. it could retain its strength up to a cherry red 1200 degrees Fahrenheit, a temperature that would melt aluminum and make stainless steel useless. The X-15 was powered by an XLR-99 variable thrust rocket engine with a thrust range from 28,000 to 57,000 pounds. Before each flight, the pilots trained 8 to 10 hours in a ground-based simulator. The X-15's flight envelope demanded precise control during all phases of flight: the powered phase, the flight out of the atmosphere, and especially the re-entry. The pilots trained for the multitude of possible malfunctions of the rocket engine, systems, and displays. The appreciation of the ground-based flight simulator was fully realized first in the X-15 program. A flight began with the pilot climbing into the X-15 attached under the wing of the B-52 on the ramp. The B-52 then taxied out and took off, slowly climbing to 45,000 feet, heading for the northeastern corner of Nevada. Once there, the B-52 turned back toward Edwards and launched the X-15. Once clear of the B-52, the pilot lit the rocket engine and began his particular flight profile, climb for altitude, for instance, or a speed run. In spite of launching in northeastern Nevada, the X-15's flight to Rogers Dry Lake lasted an average of just 10 minutes. The engine consumed the entire fuel supply in less than 2 minutes, after which the airplane was a high-speed glider with a lift-to-drag ratio of about 4 to 1. The pilot was busy the entire flight and had very little time to enjoy the scenery. Things happen fast at Mach 5+, and this was no airplane to fall behind on. Maintaining a proper angle of attack was critical if the pilot was to reach the designated altitude. Under and overshooting were startlingly easy, and both had a dramatic effect on the final altitude reached by the aircraft. The bottom portion of the ventral fin, the vertical stabilizer underneath the aft portion of the fuselage, was too tall to permit landing with it attached, so it was jettisoned moments before landing, then retrieved and used again. The X-15 had no brakes for landing, just 2 skids that popped out at the aft end of the fuselage, and a nose gear with 2 wheels that was not steerable. The X-15 came down quickly, and its pilot had only 1 chance at landing, as do shuttle pilots today. For its record speed flight, the X-15 was fitted with 2 external propellant tanks, which could be jettisoned, and covered with a silicone ablative coating painted white. Unlike the shuttle tiles, the ablative absorbed the additional heating from the high speed by charring rather than insulating. Even then, surprisingly, shock impingement around a dummy ramjet on the lower ventral tail caused some serious local damage to the skins. The ablative coating proved to be impractical for a reusable re-entry vehicle, since the old coating would have to be stripped and a new coating reapplied for each flight. With flights starting in 1959 and extending to 1968, it was and still is considered the most successful of all experimental research aircraft. The X-15 program added to the historic foundation of aerodynamics, sometimes measurably, often intangibly, in ways that were not imagined. It pushed the piloted records to an altitude of 67 miles and speed to Mach 6.7. 8 of the 12 X-15 pilots earned their astronaut wings. The X-15 provided much new insight into the once feared region of flight outside the atmosphere. It also gave engineers critical data on the unique challenge of re-entry. Re-entry compounds the effects of aerodynamics and spaceflight maneuvering and proved to be more demanding of both pilot and aircraft than anything encountered before. Many of the mysteries of re-entry flight were solved by the X-15. In sharp contrast to the high speeds and altitudes of the X-15, a strange-looking vehicle appeared at the center. The low-speed M2F1, a lifting body vehicle, had no wings and resembled a bathtub. A Dryden engineer, Dale Reed, sought to validate this new re-entry concept with a manned research aircraft. Rather than using a ballistic re-entry trajectory like a Mercury, Gemini, or Apollo capsule with very limited maneuvering range, a lifting body vehicle had an estimated landing footprint the size of California. The tubby vehicle shape was taken from re-entry lifting body shapes that were being tested at the NASA Ames Research Center. After seeing Reed's 2-foot model fly, Center Director Paul Bickle authorized an in-house effort to build the manned M2F1. In the spring of 1963, Milt Thompson made the first flight of the M2F1 towed behind a hot rod Pontiac Catalina convertible. Later, an R-4D Navy DC-3 was used for tows to higher altitudes. Flights released from behind the R-4D at 12,000 feet lasted just 2 minutes until landing. The M2F1 would lead to bigger things in the future. If the M2F1 was strange, the Lunar Landing Research Vehicle was out of this world. During the 1960s, NASA had embarked on a journey to the moon. The Apollo program's mission was to land men on the moon and return them safely to Earth. No one on the Apollo program wanted the first lunar landing, with its high pilot workload and psychological stress, to be the first time an astronaut team flew a lunar landing descent profile. To help train astronauts for this difficult task, Dryden engineers Don Bellman and Gene Matranga, along with Bell Aerospace, conceived of an in-flight simulator to train the astronauts. It became known as the Lunar Landing Research Vehicle, LLRV. The LLRV was a free-flying simulator held aloft by a turbofan jet, simulating the moon's gravity, and maneuvered with hydrogen peroxide thrusters. First delivered in late 1964, the LLRV was flown by the Dryden research pilots Joe Walker, Don Malik, and the Army's Jack Kluver. During that time, the team made significant modifications to the craft, some to better mimic the lunar module in its layout, others to make the vehicle safer or more capable. Perhaps most significant of all, the vehicle was a pure fly-by-wire craft controlled by 3 analog computers with no mechanical backup. During its 198 flights at Edwards, it had flown as long as 9½ minutes and reached a maximum altitude of nearly 800 feet. It was then turned over to Houston in December of 1966 for training the Apollo astronauts.
Picking up some dust. 4 forward.
As they say, the rest is history. On July 20th, 1969, former Dryden Center pilot Neil Armstrong set the Apollo lunar module down on the moon.
Tranquility Base here. The Eagle has landed.
The success of the M2F1 encouraged NASA headquarters to approve development of heavyweight lifting bodies, which would be launched from the B-52 and powered by an XLR-11 rocket engine. Although the lightweight M2F1 could simulate the low lift-to-drag ratio, it could not simulate the high speeds that a heavyweight vehicle could achieve. The initial program involved building 2 different vehicles, the M2F2 proposed by NASA Ames Research Center and the HL-10 proposed by NASA Langley Research Center. The first flight of the M2F2 occurred on July 12, 1966, with NASA pilot Milt Thompson at the controls. From the start, it was apparent that the M2F2 had handling problems. Several times, the aircraft rolled back and forth violently as it descended. Each time, however, the pilot was able to regain control. Despite these problems, flights continued through the remainder of 1966 and into the new year. While the M2F2 was cautiously expanding its envelope, NASA pilot Bruce Peterson piloted the first flight of the HL-10 in December of 1966. Peterson discovered that the vehicle was barely flyable. Only by keeping the HL-10 speed up was he able to maintain control. This first flight, in the words of Langley engineers, once again demonstrated the value of flight tests as proof of concept. The vehicle was grounded, while engineers at NASA Langley and Dryden could come up with a fix. Although the HL-10 was grounded, the M2F2 program pressed on. Other pilots joined the program. In May of 1967, during the 17th flight of the M2F2, the handling problems came to a head during a violent crash. The M2F2 was significantly damaged and the pilot, Bruce Peterson, was seriously injured. Peterson eventually lost an eye to the accident, but otherwise recovered. This accident became the opening scene for the 1970s hit TV series, The $6 Million Man. Following the accident, the vehicle was rebuilt in-house by Dryden technicians and renamed the M2F3. The most significant change was the addition of a center fin, which greatly stabilized the aircraft at low speeds and solved the recurring problem of poor lateral control. Analysis of flight and wind tunnel data from the first HL-10 flight suggested flow separation on the outboard fins. After the leading edges of the outboard fins were modified, the HL-10 made its second glide flight in March of 1968, and now handled as well as an F-104. In February of 1970, Air Force pilot Peter Hogue took the HL-10 to a speed of Mach 1.86, the highest speed reached by any piloted lifting body. That same month, NASA pilot Bill Dana took the HL-10 to 90,030 feet, the highest of any heavyweight lifting body. Another lifting body, the X-24A, was sponsored by the Air Force and joined the flight test program. First flown in April of 1969 by Air Force pilot Gerald Gentry, the vehicle resembled a potato with 3 fins. Its shape would be later used in the design of the X-38 crew return vehicle. The final lifting body tested at Edwards was the X-24B. This aircraft was actually the original X-24A airframe, but with a sleek new outer shell grafted on. The once potato-shaped A vehicle now looked like a flat iron with a long nose and flat underside. This design gave the X-24B a much better lift-to-drag ratio. The initial glide flight was made in August of 1973 with NASA pilot John Mankey at the controls. The earlier lifting bodies and the X-15 had all landed on the lake bed, partially due to the lack of nose wheel steering, with which the X-24B was now equipped. In August of 1975, on its 27th flight, Mankey made a precise landing on the Edwards concrete runway, demonstrating the ability of an unpowered re-entry vehicle to make a pinpoint landing. Bill Dana made the final powered X-24B flight in September of 1975, which was the last manned rocket plane flight made at Dryden. In the 1960s, the U.S. had a supersonic transport SST program in competition with the British-French Concorde SST. Dryden contributed to that program through its supersonic flight research utilizing the XB-70 and the YF-12A. The XB-70 was originally conceived as a Mach 3 strategic bomber with an operational altitude of 70,000 feet. Only 2 experimental prototypes had been built by the time the Defense Department canceled the program. The large size of the XB-70 made it an ideal test bed for joint NASA-Air Force SST research. After a tragic accident destroyed the XB-72, the program proceeded with the less capable XB-71. Though limited to Mach 2.5, it yielded data on a number of issues facing SST designers, including aircraft noise, operational problems, control system design, sonic booms, high-altitude turbulence, and correlation of wind tunnel and flight data. In a similar fashion, the Lockheed YF-12A Blackbird's ability to sustain Mach 3 cruise speeds allowed NASA to expand its research capabilities and contribute to the SST program. The YF-12 Flight Research Program generated supersonic data on aerodynamics, propulsion, controls, structures, and subsystems. It also provided critical data in other areas such as upper atmosphere physics, noise tests and measurements, materials, and handling qualities. One particularly interesting experiment focused on heat transfer and exposed an insulated and chilled hollow cylinder instantly to Mach 3 flight conditions. YF-12 flight research data was complemented by a series of wind tunnel tests, laboratory experiments, and analyses. As a result, the combined ground and flight research generated vast amounts of information that was later incorporated into supersonic aircraft design. The first flight of the F-8 digital fly-by-wire aircraft in May of 1972 by NASA pilot Gary Creer ushered in a radical new flight control concept. Until the conception of the F-8 digital fly-by-wire vehicle, mechanical systems which ranged from steel control cables to hydraulics had been used to transmit a pilot's stick and rudder inputs to the control surfaces. Although some electronic fly-by-wire systems had been flight tested, these aircraft still retain the mechanical links as backup, the Lunar Landing Research Vehicle being the exception. By the late 1960s, digital computers had become more available and offered a lighter, more capable, and flexible fly-by-wire system. Dryden engineers proposed such a digital system be developed and flight tested. The computer initially used was from the Apollo 15 Command Module digital computer, but was later replaced with 3 AP-101 general-purpose digital computers. These were state-of-the-art computers in the mid-1970s. Each had 32K of memory, operated at 0.48 megahertz, weighed nearly 48 pounds, and cost $130,000. This system demonstrated fault tolerance by continuing normal operation after certain computer failures. The amazing contributions of the revolutionary F-8 digital fly-by-wire program were quick to follow. Today, fly-by-wire is used in almost every modern aircraft, including fighters, bombers, transports, and airliners. Another F-8 was also flying at Dryden during this time, the supercritical wing aircraft. The supercritical wing grew out of Richard Whitcomb's innovative research at the Langley Research Center. The wing featured a flattened top surface with a downward curve at the trailing edge. The flattened top reduced the tendency to generate shock waves, and the downward curve at the trailing edge restored the lift loss by flattening the top. The first flight of the F-8 supercritical wing was made in March of 1971 by NASA pilot Tom McMurtry. The flight test data confirmed wind tunnel results that the wing had lower drag than conventional wings at speeds just below Mach 1. The reduced high-speed drag offered increased cruise speed, improved fuel efficiency, and a longer range. In the decades since, supercritical wings have appeared not only on airliners, but fighters, heavy transports, and business jets. The third decade was a busy period with long-lasting results. The lifting body vehicles made great contributions to what would become the Space Shuttle. Both the digital fly-by-wire and supercritical wing research opened up a new era in aircraft design. Most modern aircraft in the sky today utilize some element of design that was pioneered at Dryden during this exciting period of flight research. Just as the X-15 defined the second decade at Dryden, the Space Shuttle defined the center's role within NASA 2 decades later. The approach and landing tests of the prototype orbiter Enterprise brought a level of attention to Dryden that exceeded even that of the X-15 era. The Enterprise was to be launched from the back of a modified 747 airliner, with the orbiter gliding to a landing. The approach and landing tests, or ALT, would validate the vehicle's low-speed aerodynamics and systems, including the orbiter's fly-by-wire control system. Early in the morning of August 12, 1977, tens of thousands of visitors streamed onto Edwards Air Force Base and lined the east shore of Rogers Dry Lake to view the first free flight of the shuttle. After taxiing from the mate-demate device and taking off from the main runway, the orbiter 747 combination climbed to 30,000 feet. With the orbiter on its back, the 747 went into a slight dive, and the Enterprise gently separated. As the 747 banked to the left, the Enterprise banked right and glided to a successful landing on Rogers Dry Lake bed. Two more free flights were made in the following months, each one with the aerodynamic fairing installed on the aft end of the Enterprise, intended for use during ferry flights to Kennedy. On the fourth flight, the orbiter's fairing was removed, and the descent was steeper and faster than on earlier flights. The fifth and final free flight in October 1977 was to demonstrate a safe landing on the Edwards main runway instead of the lake bed. Each side of the runway was lined with employees and guests of Dryden for a closer view. The release and glide were uneventful, but as Enterprise neared the runway, a problem surfaced. The fly-by-wire computer system had a slight delay responding to pilot commands, and rapid control inputs led to a pilot-induced oscillation, or PIO. At landing, the vehicle touched down on the main gear, then bounced back into the air. It touched down again, and bounced again more shallowly, then touched down again, and coasted to a stop. Needless to say, the spectators along the runway, including Prince Charles, got more than they had expected. This PIO tendency was soon corrected with a Dryden-developed PIO suppression filter, that is, software changes to the flight control computer. Here, the F-8 digital fly-by-wire vehicle proved to be invaluable, testing various solutions until the best one was determined. 3.5 years later, in April of 1981, the excitement at Dryden was at a fever pitch again, with tens of thousands of spectators lining the east shore of Rogers Dry Lake, and 1,000 or more news personnel scattered around. A loud double sonic boom signaled the return of the Space Shuttle Columbia back from a 2-day mission to space. Edwards Air Force Base was and continued to be the primary landing site for the Space Shuttle until 1984. Since then, Edwards is considered the primary backup landing site for the shuttle. Between 1979 and 1982, Dryden successfully demonstrated a very unique aircraft called the AD-1. The AD-1 featured a wing that could be pivoted obliquely from 0 to 60 degrees during flight. Rather than sweeping both wings back to fly more efficiently at supersonic speeds, the whole wing of the AD-1 rotated, which greatly simplified the mechanical design. While the AD-1 was not specifically designed for high speeds, it demonstrated the concept for a possible future high-speed design. During this decade, aircraft efficiency became more important with the increasing cost of fuel. Projects like the KC-135 winglets and active and passive laminar flow control projects on the Jetstar, the F-111 and F-14 aircraft were explored. While laminar flow control concepts have not been used yet on commercial transports, winglets have had wide use on many Boeing and Airbus airplanes. New technologies for fighter aircraft were also being tested in this decade using two small remotely piloted aircraft called HIMAT, Highly Maneuverable Aircraft Technology Vehicles. Only 23.5 feet long, it featured a close-coupled canard and an aeroelastic tailored composite wing, technologies used later in this decade on the X-29. The digital fly-by-wire control system used an autopilot to fly precise maneuvers to gather large quantities of quality data in a short time. HIMAT research brought about far-reaching advances in digital flight control systems, which can monitor and automatically correct potential flight hazards. The HIMAT successfully achieved its goals of a 100% increase in aerodynamic efficiency over 1973 technology and maneuverability that would allow a sustained 8G turn at 0.9 Mach and an altitude of 25,000 feet. By comparison, at the same altitude and speed, an F-16's maximum sustained turning capability is about 4.5 Gs. As a tribute to the HIMAT contributions, one vehicle now hangs in the Smithsonian Institution's National Air and Space Museum. In 1984, NASA and the Federal Aviation Administration, FAA, teamed up for a flight experiment called the Controlled Impact Demonstration, or CID. The project's goal was to crash a Boeing 720 airliner to test a fuel additive designed to suppress post-impact fire. The additive, called anti-misting kerosene, or AMK, demonstrated the ability to inhibit ignition and flame propagation of fuel in simulated crash tests, but researchers knew an actual crash would provide more realistic conditions. A special site was constructed on Rogers Dry Lake, and cameras were set up to document the test from every angle, including inside the passenger cabin for even more crash data. On December 1, 1984, with only test dummies, extensive instrumentation, and 76,000 pounds of AMK on board, the old Boeing jet, flown remotely by a Dryden pilot, Fitz Fulton, was crashed onto the specially prepared area of the lake bed. When the aircraft touched down, iron posts embedded in the lakebed tore open the fuel tanks. The results were surprising. The CID impact ended with a spectacular fireball, enveloping and destroying the aircraft and everything in it. With the FAA on the verge of requiring all U.S. commercial airlines to use AMK, the NASA test discovered that the additive didn't work. Once again, the benefit of flight test was realized. The X-29A forward swept wing program marked the return of the X-planes to Dryden after a 9-year absence. The two-phase program ran from 1984 to 1992. The first phase concentrated on the proof of concept at low angles of attack and high speeds. The second phase of the X-29A program, the high angle of attack tests, is covered in the fifth decade. Two X-29A aircraft were built as technical demonstrators to test a forward-swept wing with advanced composites, variable camber, and a thin supercritical airfoil. Also tested was highly unstable and highly augmented multi-surface controls that required an extremely high-gain, triple-redundant digital control computer with analog backup. The fiber strands of the composite aeroelastic tailored wing on the X-29A were specifically aligned to allow it to twist under load. The twisting relieved the loads at the tip, preventing structural divergence or breakage at high speeds. The digital flight control computer system provided sufficient artificial stability and predictable handling qualities in a very unstable aircraft. Moreover, its supercritical wing contributed to good maneuvering and cruise characteristics in the transonic range. Despite these accomplishments, the predicted higher lift-to-drag ratio did not materialize, being about equal to or slightly less than the then-current fighter aircraft. The fourth decade brought much publicity to Dryden with the space shuttle flights, controlled impact demonstration, and the revolutionary X-29A. Each of these projects came to Dryden from outside agencies for the world-class expertise and facilities. All were successful, though not always in the way expected. In the words of Hugh L. Dryden, flight research separated the real from the imagined problems and made known the overlooked and the unexpected.
Down we go. 40, 50, 60. This is going to be a wild one. 75.
During the fifth decade at the NASA Dryden Flight Research Center, the F-18 High Angle of Attack Vehicle, or HARV, X-29A and X-31 explored the region of high angle of attack extensively.
Stick forward. 30,000. Stick neutral. Okay, I've got it. 7,700. Out to the right.
Historically, most combat aircraft easily lost control in this flight regime and frequently entered an undesirable spin. Angle of attack limiters were often implemented to prevent flight in potential spin regimes. The F-18 HARV was the number 6 pre-production F-18 aircraft and had been used previously by the Navy for spin testing. It was brought to Dryden in pieces on a flatbed trailer. It had been cannibalized and was missing over 400 parts. Dryden mechanics and technicians restored the F-18 and named it Silk Purse to indicate its transformation from a sow's ear carcass of missing parts. The F-18 HARV was flown in 3 configurations: the standard F-18 with thrust vectoring, and with thrust vectoring and actuated four-body strakes. Data was gathered on aerodynamics, controls, and propulsion.
Oh, that's great.
The HARV project produced some of Dryden's best surface and smoke flow visualization.
Nose coming down slow.
The flow visualization and surface pressure data was used to improve and validate computational fluid dynamics, CFD, and wind tunnel research. The thrust vectoring greatly improved the handling qualities at high angles of attack, and the HARV easily achieved its design point of 70-degree angle of attack in stabilized flight. Thrust vectoring also greatly enhanced the maneuverability of the HARV in mock aerial combat. The actuated nose strake concept proved to be a powerful and precise yaw control device at high angles of attack. The HARV program successfully developed new control design and handling qualities criteria for high angle of attack flight. The X-31 was the first international X-series aircraft with an international test team consisting of DARPA, the U.S. Navy, the German Ministry of Defense, Rockwell International, and Deutsche Aerospace. As the complexities of the program increased, Dryden and the Air Force joined the team, and the personnel and aircraft were moved to Dryden. The X-31 was designed for super maneuverability and used lightweight graphite epoxy thrust vectoring vanes instead of the heavy Inconel metal vanes of the HARV. The aircraft could perform controlled rolls at 70 degrees angle of attack and post-stall 180-degree turns at minimum radius, a maneuver known as the Herbst maneuver or J-turn. It performed many mock aerial battles with Dryden F-18s and Nellis F-15s and F-16s. As a final show of its capability, the X-31 demonstrated its exhilarating post-stall maneuvering at the Paris Air Show in 1996, creating quite a stir.
So cool. Holding and recovering. 700 feet, rolling into the slow speed.
In contrast to the F-18 HARV and X-31, the X-29A vehicle exhibited good high angle of attack characteristics without the need for thrust vectoring. At 45 degrees angle of attack, the vehicle demonstrated much better than predicted control and maneuverability. At high angle of attack, the flow on the wingtips of a forward swept wing remains attached and the ailerons remain effective. Conversely, for a conventional swept-back wing, the wingtip flow becomes separated before the rest of the wing and the ailerons quickly lose effectiveness. Even at 67 degrees, the maximum angle of attack achieved, the X-29A displayed limited control. The flight research into laminar flow control at Dryden culminated an experiment on the F-16XL No. 2. Active and passive laminar flow experiments had been tested previously on the F-104, F-111, F-14, F-18, Flight Test Fixture, Jetstar, and the F-16XL No. 1. For the proposed high-speed civil transport, laminar flow control offered the single most significant potential improvement in lift-over-drag ratio of all the aerodynamics technologies considered. A successful application could result in significant benefits in reduced takeoff gross weight, fuel burn, cruise drag, engine size, emissions, and sonic boom.
We're going to be on your your left side, taking some pictures of the glove, Dana.
On the F-16XL number 2, a titanium glove perforated with millions of microscopic laser-drilled holes was attached to the left wing. Air was drawn through the tiny holes through ducting to a suction pump in the fuselage. This process results in a smooth laminar boundary layer on the surface and results in much lower friction drag than the normal turbulent boundary layer. Flight test results showed that laminar flow was successfully achieved to nearly the goal of 50% chord. In the support of the Space Shuttle program, a Convair CV-990 aircraft was modified to test Space Shuttle tires at various loads, side slip angles, and landing speeds. These tests were performed to expand the landing envelope of the shuttle. A specially designed landing gear was manufactured and installed between the main gear of the CV-990 and could simulate vertical loads of up to 150,000 pounds, side slip up to 15 degrees, and landing speeds up to 240 knots. A series of tests with the CV-990 were conducted at Edwards and at the Kennedy Space Center, Florida in 1993 and 1994. The tests demonstrated that the crosswind limits on the orbiters could be safely increased from 15 to 20 knots, expanding the orbiter's landing options. The Dryden tests also resulted in changes to the runway surface roughness at the Kennedy Space Center. During the mid to late 80s and early 90s, a series of integrated flight propulsion control research experiments were performed on a NASA F-15. The standard analog control augmentation system, CAS, was replaced with a digital electronic flight control system, but not replacing the standard mechanical flight control system. The engines were also specially equipped with digital electronic engine controls. Projects like the Highly Integrated Digital Electronic Control Project and Performance Seeking Controls Project demonstrated significant improvements in thrust, range, and engine life could be achieved by integration of digital flight, engine, and inlet control systems. The F-15 also successfully tested a self-repairing flight control system, where a control system failure could be detected, isolated, and the control system reconfigured to obtain satisfactory aircraft performance. This particular technology holds significant promise for survivability in a hostile environment. In July 1989, a McDonnell Douglas DC-10 airliner lost all means of conventional control when its tail-mounted engine exploded at 37,000 feet, severing the aircraft's hydraulic lines. The crew learned in real time how to control the aircraft by varying the thrust on the two remaining wing-mounted engines. With emergency equipment waiting, the crew attempted to land at the Sioux City, Iowa airport. Although the flight ended in a fiery crash, nearly two-thirds of the passengers survived, due largely to the crew's heroic efforts. The accident inspired a Dryden engineer, Bill Burcham, to initiate a new project dubbed Propulsion Controlled Aircraft, PCA. Burcham envisioned software that integrated engine thrust with the digital flight computer to control the aircraft. During flight tests, engine thrust was commanded by the PCA software to respond to the pilot's control inputs, which he made using small thumb wheels on the mode control panel. In April 1993, NASA pilot Gordon Fullerton successfully landed an F-15 using only the engines with the PCA system. Following that success, in August 1995, the program reached its zenith. This time, Fullerton demonstrated the PCA system in a series of successful landings using only engine power for control on a McDonnell Douglas MD-11 airliner. While much of Dryden's research during this decade focused on high angle of attack programs, significant advancements were made on space shuttle tires and on the benefits of integrating digital flight and engine control systems. The sixth decade brought a new focus to Dryden. In addition to atmospheric flight research, a series of space-related projects and unpiloted vehicle concepts were initiated. The Ames DC-8 and ER-2 airborne science aircraft were also transferred to Dryden in 1997, beginning a new era of Earth science research. F-18 Active Aeroelastic Wing, or AAW program, investigated the benefits of aerodynamically twisting flexible wings to improve roll maneuverability of high-performance aircraft at transonic and supersonic speeds.
Ready? Mark. Complete.
This wing warping concept is similar to the technique the Wright brothers used on their early flyers. The F-18's wings were modified to increase their flexibility by replacing the wing covers with thinner ones. Leading-edge flap actuators were added to the wing to operate the outboard segments separately from the inboard segments. To accommodate these changes, the flight control computer software was modified. Conventional use of control surfaces at high speeds can result in unfavorable wing twisting and reduce control from a phenomena called aileron reversal. AAW used the outboard leading-edge flaps and existing ailerons to impart the aerodynamic force necessary to provide the desired roll force.
Complete. Paddle off.
AAW control technology can substantially increase control power and reduce aerodynamic drag and aircraft structural weight in future aircraft. A derivation of the self-repairing flight control system program a decade earlier, the Intelligent Flight Control System, or IFCS, flown on a highly modified F-15, incorporates the earlier program's self-learning concepts into flight control software. Using a neural network, it is capable of manipulating far more control surfaces at a faster rate than the first-generation self-repairing flight control system.
Neural nets are engaged. Clear for failure. Failure.
But IFCS technology is capable of more than simply making a damaged aircraft flyable. For example, intelligent flight controls could lead to rapid prototyping of aircraft control laws. The Autonomous Formation Flight, or AFF program, extended the symbiotic relationship of migrating birds by exploiting the performance benefits of aircraft formations. The traditional V formation allows all birds but the lead to reduce drag and conserve energy. Using differential GPS to guide AFF pilots into position, a NASA FA-18 flew in the wing upwash generated by a lead FA-18 and demonstrated a 14% fuel savings at cruise altitude, better than the project goal of 10%.
And strong effect right there. Started to roll the right slightly.
The Automated Aerial Refueling Project, AAR, an outgrowth of the Autonomous Formation Flight Program, evaluated the capability of an FA-18A aircraft as an in-flight refueling tanker for unmanned air vehicles. The project focused on developing accurate analytical models derived from actual flight test data to aid in development of an autonomous aerial refueling system.
Okay, this one's very smooth and it's not deviating left or right at all. Copy. The positive closure, a little low, coming up, coming up. She's got it, she's got it.
The first ever autonomous probe and drogue airborne refueling operation was successfully performed on August 30th, 2006 by the Autonomous Airborne Refueling Demonstration, or AARD project.
Okay, we're in.
Pilots were on board the receiver FA-18 for safety purposes and to fly the aircraft to initial test conditions.
No, you need to come in another 10 feet.
A global positioning satellite-based relative navigation, coupled with an optical tracker, provided the precise positioning required to put a refueling probe into the center of a 32-inch basket dangling in the airstream behind an airborne tanker. As a testament to the autonomous system, Dryden pilot Dick Ewers and flight test engineer Marty Trout assumed a look-ma, no-hands position on the final refueling demonstration.
Okay, a nice smooth closure of the basket, slightly moving.
As important as the successful engagements, the system also identified and safely recovered from each missed
Okay,
attempt.
it detected a miss and came back on its own, so I did not do anything.
Projects like the AFF and AARD have helped to establish Dryden's leadership in autonomous aircraft development and flight research.
She's got it, she's got it.
And we have 5, 4, 3, 2, 1. Launch, launch, launch.
Requires.
The X-38 prototypes mark the return of lifting bodies to the Dryden Flight Research Center.
10,000 feet.
Like the X-15 and previous lifting bodies, the prototypes were dropped from the center's venerable B-52B bomber. The X-38 Crew Return Vehicle, or CRV, was conceived as a lifeboat for the International Space Station. The X-38 was largely based on the X-24A, although its landing profile would differ significantly. Once the X-38 CRV had entered the atmosphere and slowed to subsonic speeds, it would deploy a large parafoil for landing. During flight tests guided by a GPS autopilot, the X-38 prototypes demonstrated precise touchdowns on the dry lakebed at Edwards Air Force Base. Research flights of the prototypes were conducted from 1998 through 2002, when the program was canceled due to changes in space policy. Other next-generation space vehicle demonstrators met a similar fate. The Lockheed Martin X-33 Venture Star was designed to research the flight characteristics of a full-scale reusable launch vehicle. The X-33 was a fully reusable single-stage-to-orbit vehicle that was to operate much like an airliner. The Orbital Sciences X-34 technology testbed vehicle was developed to demonstrate key technologies that could be integrated into the reusable launch vehicle program. Both programs were canceled in 2001 before either had a chance to fly. Research platforms of the early 1990s did not satisfy many of NASA's altitude and endurance requirements for Earth science missions. NASA created a program to mature the technologies necessary to seed the uninhabited air vehicle UAV industry and use this new generation of aircraft for high-risk experiments that were previously not feasible for manned missions. The program was called the Environmental Research Aircraft and Sensor Technology, ERAST. Two such aircraft were the turboprop-powered General Atomics Aeronautical Systems, Inc., Altair Predator B, and the piston engine-powered Aurora Flight Sciences Corp Perseus B. Both of these ERAST aircraft were remotely piloted and designed to fly as high as 60,000 feet and on missions lasting up to 24 hours or more. Less conventional ERAST UAVs included the many solar-powered flying wings built by AeroVironment Inc. Pathfinder Plus and Helios prototypes were just two of these aircraft and were used for such missions as observing crops, monitoring shoreline, testing communications, and providing new sea detect and avoidance technologies which allows UAVs to steer clear of other aircraft.
Go ahead, NASA 2.
We've been watching you bounce around 96.5 for quite a while now, and I think it's time to probably call it a record flight. Congratulations, I think it's time to turn around.
The Helios prototype achieved an ERAS goal by reaching an altitude of 96,863 feet in August 2001. As part of NASA's Airborne Science Program, Dryden used a modified DC-8 aircraft as a flying laboratory to collect data in support of experimental projects serving the worldwide scientific community. Originally based at the NASA Ames Research Center, the Airborne Science aircraft were moved to Dryden in 1997.
Okay, we're level at 250, stable at 420.
Actually, we want to hold this altitude.
The DC-8 flies three primary types of missions: sensor development, satellite sensor verification, and basic research studies of the Earth's surface and atmosphere. The DC-8 has flown all over the world, allowing scientists to successfully address today's planetary issues, including global warming and deforestation. In 2006, the University of North Dakota began operating the DC-8 under contract to NASA. Dryden flies two Lockheed ER-2 Earth Resources research aircraft as high-altitude flying laboratories in the Suborbital Science Program under the agency's Science Mission Directorate. Like the DC-8, the ER-2s were moved to Dryden from Ames in 1997. The aircraft collect information about our surroundings, including Earth resources, celestial observations, atmospheric chemistry and dynamics, and oceanic processes. The aircraft also use electronic sensors for research and development, satellite calibration, and satellite data validation. Since the Airborne Science Program's inaugural flight on August 31, 1971, NASA U-2s and ER-2s have flown more than 4,500 data missions and test flights to support the scientific research endeavors of NASA, other federal agencies, states, universities, and the private sector. Since the late 1950s, the supersonic combustion ramjet has been seen as the means to achieve low-cost access to space and high-speed transportation. The scramjet can operate between Mach 5 and near orbital speeds. It is far more efficient than a rocket, as it burns oxygen from the atmosphere rather than having to carry its own supply. But while the potential of a scramjet is great, so are the engineering difficulties. After some 4 decades of study and ground research, the technology was ready for an actual flight of a scramjet-powered aircraft.
3, 2, 1, launch.
Sequencer reset.
The X-43 made aviation history in March of 2004 with the first successful flight of a supersonic combustion ramjet or scramjet-powered airplane at hypersonic speeds, speeds greater than Mach 5 or 5 times the speed of sound. After being dropped at 40,000 feet from the B-52, the X-43 was accelerated up to near Mach 7 and 94,000 feet by a Pegasus booster.
Ready to set.
Ready to set.
Sep.
Separation.
The X-43 then separated and operated its scramjet for approximately 11 seconds. During this time, the X-43 accelerated and achieved performance very close to the pre-flight predictions.
RV is stable at this time.
The next and final flight of the X-43A introduced greater unknowns. Unlike the previous flight, the scramjet engine could not be ground tested at Mach 10 for the complete burn because wind tunnels could only simulate those conditions for 1,000th of a second at a time. Computer analysis predicted that the aerodynamic heating at Mach 10 was twice that at Mach 7. For this flight, additional thermal protection in the form of reinforced carbon-carbon composite material had to be added to the leading edges of the X-43's vertical fins.
Launch on my mark.
In November 2004, the X-43A and Pegasus were dropped from the B-52. After being accelerated to Mach 9.6 and 109,000 feet altitude, the vehicles separated and the X-43A successfully sustained the desired cruise speed. Again, the flight data correlated well with pre-flight predictions.
The RV is stable at this time.
NASA Dryden remains the premier aeronautical flight research center of the nation, and not simply because of its location and accomplishments. Over the decades, with a can-do attitude, it has developed an extraordinarily knowledgeable workforce with diverse specialties. From subsonic to hypersonic aerodynamics, atmospheric to exoatmospheric physiology, powered and unpowered, as well as piloted and unpiloted aircraft. In the process, Dryden has pioneered a host of new technologies and methodologies related to aeronautics. Its engineers have been awarded patents and national research awards, and its pilots have been recognized with Collier and Harmon trophies. Just as important is Dryden's vast experience in developing and executing all manner of flight research programs, small and large, national and international, in-house or through partnerships. These are the attributes that continue to make Dryden the place to come for world-class flight research.